How's everybody doing? Professor Bryant back with another installment of Workout Wednesday. Today, our focus is going to be on KSP, solubility, product constant, and the applications of KSP. We're going to first do some simple calculations of KSP and then move from there. So I'll be uploading this worksheet over KSP. It's a really good worksheet, gives you some tips as well as some of the answers. So we're going to work through question 5. I think it's four or five different parts in question 5. So the first question is calculate the molar solubility of cadmium hydroxide in plain water at 25 degrees Celsius, and then calculate the pH of the saturated solution at equilibrium. I will also be uploading the KSP table from the text. I took a picture of it, Chem scanner, and I will be placing that into the reference materials. This will be the reference materials that we use for any of the assessments. You can also use that for your homework, etc. So if we look for cadmium hydroxide, we see that the value is 2.5 times 10 to the negative 14. Okay, so if we remember anything about our equilibrium of slightly soluble salts, we remember that we're dealing with an equilibrium expression that involves two hydroxides and one cadmium ion, where each of these hydroxides is negatively charged, right? We know that KSP, or we should know that KSP is equal to CD2 plus times concentration of OH squared. Okay, now if we think about this from the determination of equilibrium, we should recognize that when we're dealing with an ice table in this example, solids are not involved, and we start with 0, we add 2x of each of these, and then we end up with x times 2x. And if we plug this into our KSP expression, we end up with x times 2x squared, and that ends up giving us KSP is equal to 4x cubed, which means that x is equal to the cube root of KSP over 4. Now, how do we calculate that? So the KSP value is equal to 2.4. What did I say? Hold on. Let me double check that. Is 2.5 times 10 to the negative 14 times 10 to the negative 14. Okay. Now, from a calculator perspective, for those that are not familiar with the cube root, what we would do is math, and then down here, number 4. So 3 cube root, and then if we plug in our KSP to the negative 14 divided by 4, and I would always suggest placing parentheses, then we end up with 1.8 times 10 to the negative 5, right? 1.8 times 10 to the negative 5. So x is equal to cadmium 2 plus concentration, which is equal to the concentration of the entire molecule, right? Because we have a 1-to-1 ratio, which is equal to 1.8 times 10 to the negative 5. Okay, so that is molar solubility. Anything that involves this guy is when we hear and see molar solubility. The concentration of cadmium is this, and obviously the concentration of hydroxide is equal to 2x, which is equal to this value times 2, which is equal to 3.7 times 10 to the negative 5, approximately. Okay, so the molar solubility of the entire compound here, hydroxide here, cadmium here. Now, I've done a step ahead because this is part A. Second part B says calculate pH. Well, now that we know the concentration of OH in solution, remember, hydroxide ion is a strong base, so therefore we can calculate pOH is equal to negative log of 3.7 times 10 to the negative 5, negative log of second answer, And that gives us a pOH is equal to 4.43. Therefore, the pH is equal to 9.57. So here we've solved. I've set up the equilibrium expression, showed you the KSP expression. This is from the reference materials. And then I solve for X using the cubed root. X gives us the molar solubility. Hydroxide, however, needs to be determined because of 2X based on equilibrium, and then we can determine pH from there. So that is parts A and B. So let's move on and take a look at some of the next portions of the questions. Okay, so part 5C asks us, what is the molar solubility of cadmium hydroxide in a buffer solution? Okay, a buffer solution obviously means that there may or may not be hydroxide ions already in solution. They have told us that the buffer solution has a pH of 9, and they give us a hint, right? Calculate the hydroxide that is already in solution. That's what they mean by outside in the buffer. How much is already in solution? And then part D says calculate the molarity or molar solubility at a different pH. So let's first talk about molar solubility at pH equal to 9. Okay, so if we are still dealing with the exact same system, and I'm going to just rewrite this. Cadmium 2 plus in solution plus 2OH minus in solution. Okay, so they're telling us that the pH of the buffer is equal to 9. Therefore, the pOH is equal to 5. Therefore, the concentration of hydroxide is equal to second log of 5. And that is second log -5. And that is 1 times 10 to the -5 molar. Already in solution, right? Already in solution. So, because of that, we must take that in consideration when we're dealing with our ice table. So I just did a little calculation over here. Remember, we're never worried about the solid in the ice table. Now, before any equilibrium is established, we're saying we don't have anything dissolved, but we do have 1 times 10 to the -5 molar already dissolved here. We're also saying that we're adding cadmium and we're adding 2x of the hydroxide, and now we end up with a situation where 1 times 10 to the -5 plus 2x. Remember our KSP expression up here. We now need to use that KSP expression, but we need to make some assumptions. If KSP is equal to cadmium 2 plus and hydroxide squared, we need to recognize that cadmium 2 plus concentration is X in this scenario, and hydroxide concentration is 1 times 10 to the -5 plus 2x squared. Now, one thing that you immediately recognize is that this is going to give you a cubic, and we haven't done any solving a cube root. So this is one place where you can remember that as soon as you start seeing that situation, that's not like the problem before where we can take a cube root. This gives us an equation that is no longer just x cubed. But the more important thing to remember is that this is going towards 0. And the reason for that is that we know the KSP for this is very small, right? Times 10 to the -14. That means that the amount of hydroxide that is going to be dissolved from our solid is so minuscule that it really is not going to impact this value. It's actually much, much less than 1 times 10 to the -5, which means that we can actually treat this as x times 1 times 10 to the -5 squared. Now we can solve for x using KSP, and we see that x is equal to KSP all over 1 times 10 to the -5 squared. And that's equal to 2.5 times 10 to the -14 all over 1 times 10 to the -10. And therefore that x gives us 2.5 times 10 to the negative 4, which is equal to cadmium 2 plus concentration, which is also equal to the molar solubility of our salt, right? Of our salt. So we have a molar solubility now that is a different value than it was in water alone. Okay. Now, the next question